All right, well, let's get started here. A couple of announcements to begin. Thursday, we are not going to have a live class meeting. That will be recorded, and I'll email you the link and post it on. Oh, did I say Friday? It's Thursday. I don't know. In my mind, for some reason, I think I said Friday. Class on Thursday is pre-recorded. And so I'll send you the link for that, and the link will also be on Blackboard, but we won't have any live lecture for Thursday. You've just submitted homework number 3, and I've sent the solution to the grader. She'll get started on that right away. I hope that you are taking advantage of the comments that she posts on your assignments. It takes a little bit of extra time to do that, but it, I think, makes it a lot easier to learn from your mistakes and identify maybe if you've done something wrong. So please take the time to review your graded work. Your next assignment's not due until Tuesday of next week, so you've got a week to do that. It's available now. And then next Thursday, we're going to have our first midterm exam. And so the midterm exam is going to be a like short answer kind of calculation type problems. It's not multiple choice. What I generally do is give 3 or 4 questions that have, similar depth to the homework problems, so not way harder and not way easier. And so I still need to look at the schedule for everybody in the class to make sure that what I have in mind will work out. But probably what I would do is I would make that exam available starting at, for example, like 10 a.m. And then I would give you until like 1 p.m. to submit the exam. And so I know that everybody here is available from 11 until 12:15. And so the extra time on either side of that would just be related to, if you need to print out the exam or if you have any technical issues. Now, you don't necessarily have to print the exam. You can solve it on a blank piece of paper and then just scan that and send it back to me. But, that's just what I'm envisioning right now is even though the exam is intended to be finished in 60 minutes, you're going to have well in excess of 60 minutes to take the exam. So are there any questions about that or any of the other announcements before we move on to today's topic? All right, well, if you do have any questions, then please feel free to send me an email or give me a call on Teams. Of course, I'm going to see many of you during lab this afternoon and tomorrow, so we can also talk about it then, but just get in touch if you have any questions. All right, so in the last couple of classes, we've been talking about hydrostatic forces on flat surfaces, and now we'll translate some of those lessons that we've learned into computing the magnitude and location of hydrostatic forces on curved surfaces. And for us to understand how to do hydrostatic forces for curved surfaces, I want to remind you about the idea of projections. And this is probably something that you were exposed to previously in your CAD class. And the idea with the projection is that you are representing an object that has 3 dimensions with a flat drawing. And so you would have maybe a side view and a top view and a view from a different side. And a projection is just kind of a flat 2-dimensional representation. And so take, for instance, if you are doing like shadow images on the wall. And so you can see here, somebody has their hands configured in a way that the hands are 3-dimensional, but what is projected onto the wall looks like a rabbit and it's flat. And this is a vertical projection, meaning that the image that you get is because there's a light that's shining its photons towards the hand, and those photons are traveling horizontally. And so the light maybe is where we are, so, or maybe off to the left side a bit, because you can see that the shadow is cast towards the right. So that would mean that the image is to the left side of the hands. The idea, though, is that the photons are traveling horizontally, and then the surface upon which that projection is projected is a vertical surface. And so what we're looking at is a vertical projection. Simple idea, right? So think about a more complicated shape. And we can have this object, and if the light is coming in from one side, we can think about the projection as the shape that the shadow would cast. And so you can see that there's a flat piece across the top that has a corresponding horizontal line on the projection. And so this idea of projections is important for us because we're going to use it to determine the magnitude of the horizontal force on a curved shape. And for curved shapes, we're going to have to consider the forces in two different directions. And so this idea of projections we employ in order to determine the horizontal hydrostatic forces. Now this is the type of problem that we will try and solve. You can see that AB is a curved surface. And so maybe what it is a flat plate of metal that was bent into a quarter circle shape. And so that curved gate, we would want to know what's the magnitude and the location of the forces that are acting on it. Sometimes we say line of action to describe the location of the forces. And line of action specifically means where is it located and what direction are the forces acting. So all three of those things are important. How big is the force? Where is the force applied? And what direction is the force applied? And the reason why we need to know those things, for example, is we may have to check how strong is the weld at B, because presumably this is a surface that goes into the page. And so there's going to be a connection stress at location B. And likewise at location A, we're going to have to know how strong is that attachment point compared to the forces that are being applied. And you know, if the forces are greater than the strength of that attachment, then there's a risk that it may fail and that the water would come spilling out. So that's a little bit of background on why we care. And so in a process like this, some of the questions that we'll need to ask just to investigate what's going on is, you know, from the drawing dimensions or just by inspection, you might be able to identify what's the shape of the curve. So in this case, you can see that it's a quarter circle that goes into the page. And so if you're looking on the monitor here, it would be similar to if I had a flat piece of paper and then I curve part of it upwards. Okay. So that's the shape of it. We may need to find out, you know, what are the depth dimensions, because the deeper we go, the higher the pressure will be on that surface. Also, where does the curve intersect the straight surfaces? And so we're going to want to know not only how deep is it to the curve itself, but then what are the dimensions of the segments above it. And the radius of the curve, that if this is a quarter circle, then we'd want to know how far is the radius of curvature there. So now you can see in this sketch, some of those answers are being addressed in the dimensioning. Okay, so you can see that it's a quarter circle just by looking at the fact that if you extend horizontally a line outward from B and then vertically a line outward from A, they intersect at point C, and the shape seems to be consistent with the sweep of a 2-meter radius. And so if you follow that dimension down, you can see that it's 2 meters from C to B, and it's also going to be 2 meters from C to A. So that's kind of the implications of it being a quarter circle. Also off to the side, we have the dimensions of 4 meters from the water surface down to where the curve begins. So that 4 meters of depth is important because that's going to be adding to the pressure on AB. I already mentioned the radius of curvature, and we got that dimension here in the top. And that also sweeps downward from CA. And then it's helpful even if the drawing doesn't have points labeled. You know, like if this was the original drawing that you were given, it might be useful to sketch out what is the shape of what's above that gate. And so to sketch out the quarter circle, to sketch the rectangle that's above the gate, because those shapes are going to have to be accounted for because there's a certain weight of water above the gate. And it's the weight of the water that contributes to the vertical forces. So I already mentioned the horizontal forces are due to the projection, and the vertical forces are from the weight of the water. So that's kind of a preview of how we're going to handle the forces on a gate like AB. Let's look at it in particular. Let's look at the specifics if we assume that gate AB extends 1 meter into the page. So the image that we're looking at, it has 1 meter of dimension into the page. And so, you know, for example, that means that there's a rectangle up here, B, C, D, E. And so the dimensions are 2 meters of height, excuse me, I said that wrong, 4 meters of height, 2 meters of width, and then 1 meter into the page. And so there is this box of water that's 2 by 4 by 1. And now think about the shape of this quarter circle and what that looks like if you extend it 1 meter into the paper. It's kind of like a pie shape or a wedge that's above that gate. So what we're going to do is try to find what force is required to hold the plate steady. So you can see F down here at the bottom is going to be the magnitude of the force that holds the plate steady in response to the vertical force of the rectangular shape. So that's the weight of the water inside of that box. And then the weight of water in the wedge. And then there's also a hydrostatic force pushing in from the side. And so the resultant external force that's required to hold the system steady is going to resist both of the vertical forces and also the horizontal force. So does everybody understand so far these arrows and what they represent? Feel free to interject with any questions or comments if you've got them. This is an important example. All right, so here are the labels. FV is going to be the weight of the water above surface BC. FH is the horizontal forces acting on the vertical projection. And so now think about when we were talking earlier about shadows and projected shapes. If we have AB, then what does the vertical projection of that look like? So remember earlier I held a piece of paper up and I said the gate is like if you take a flat piece of paper representing like a metal plate and then you bend that and now it's a quarter circle. So you're looking at in the webcam there a quarter circle. And so the vertical projection says, what does that look like from the front? So it's a curve from the side, but from the front it just looks like a rectangle. So does anybody know what's the dimensions of the projection, vertical projection of AB? Maybe you could type it into the chat box there. What is the dimension of the vertical projection of AB? Something by something are the dimensions. 2 by 1. That's right, Caleb. So it's 2 meters tall and 1 meter wide. Of course, we don't see the 1 meter of width looking at it from this view, but if we change our perspective and we're looking at the gate from the front, then we would see 1 meter of width. So to find FH, we're going to act as though this hydrostatic force is acting on a vertically oriented gate that is 2 meters tall and 1 meter wide. So to find the F overall, the force required to hold the system steady, it's going to have a vertical component and a horizontal component. And so we're going to find its constituent pieces and then find the resultant magnitude from that. All right, now here is the numbered step-by-step approach that we will follow. First thing is we'll find the horizontal force. So I just told you, let's pretend that there's a gate, CA, and it's 2 meters tall and it's 1 meter wide. Now you've already got a lot of experience calculating the hydrostatic forces on vertical gates. Remember, if it's vertically oriented, then that's easy because Y bar and delta H are the same thing. So before anything else, what I'd like to do is I'd like to pause and ask you to calculate what is FH, both what's the magnitude of it and also what's its location. All right. So I'll pause the recording for now and give you a moment to calculate the hydrostatic force magnitude and also the location for F sub H. All right, well, let's look at the solutions here. All right. Okay, so step 2, the vertical forces. Let's see here. All right, so the, let me just expand this all the way. Okay, so we already found the horizontal force. Now the vertical force due to this cube of water, it has a volume of 2 by 1 by 4. So it's volume times gamma in order to determine that the weight of that amount of water is 78,480 newtons. So that's a force that's acting down on the gate simply because of how much water is above it. And likewise, there's a cumulative effect where the weight of the water that comes from that wedge shape is also bearing downward on the gate. And so that shape is a quarter circle multiplied by whatever depth into the page we have. So the area of a circle is pi r squared, and the area of a quarter circle is 1/4 pi r squared. So 1/4 pi r squared times 1. So this gives us the volume, and then multiplying it by gamma turns the volume into a force. Because remember, gamma has units of newtons per meter cubed. So in this case, the area of the circle is 3.14 meters squared times 1 meter into the page. Now makes that a volume times 9810. So it's 30.8 kilonewtons is the vertical force W. So that's acting down, and the FV is acting down. By the way, I think now is a good time for me to ask, there's something about W that's different from FV. Check out the location where they have placed FV. Looks like it's in the center. So you notice it looks like it's right in the middle between C and B. So that's FV. But what about W and the location of that? What do you notice about the placement of that force? Like, how is it being represented side to side speaking?
Is it at the centroid of that quarter circle?
Good, it is. So it's at the center of area for the quarter circle, and that's not in the middle. You know, there's a whole piece of this shape missing over on the right side, and so that pushes the center of area for what remains to the left. And so whereas it was 1 meter from C to the force, it's going to be less than a meter from this CA plane over to where the force W is located. So it's not right in the middle because it's at the center of the area for a quarter circle. So we will talk about that when we talk about the line of action, but since we've now calculated the magnitudes, I just wanted to briefly address that topic of its location as well. All right, so any questions so far with where we're at on this example? All right, step 4 was find Fx. Now what I mean by Fx is it's this horizontal force component of the resultant. So if FH, as we just calculated up above, FH is 98.1 kilonewtons. Fx is going to be the opposite direction and the same magnitude because that's the only horizontal force that there is. Now the arrow is pushing to the left, and so that's already identifying the direction of the force. So as long as I have the direction defined with my sketch, then I don't need to say that Fx is negative 98.1 kilonewtons. That would be redundant. So you can see that I have an arrow here, and I'm saying that the horizontal component of the resultant force required to hold the system steady is to the left with a magnitude of 98,100 newtons. So whether I write a little statement off to the side clarifying that I mean to the left, I probably should do both. You know, I should have the arrow showing that it's to the left, and then I should also say, like in parentheses, the force Fx is to the left, just to make it explicitly clear. All right, now what about the vertical forces, Fy? So it's just going to be the sum of Fv and W. So Fy, how much do we have to push up on that gate? We have to push up on that gate enough to hold the weight of the water that's above it. So it's going to be the sum of the vertical forces. So it is the sum of the 98.48 kilonewtons that came from the rectangular shaped box, and then the 30.8 kilonewtons that comes from the wedge shaped quarter circle that's immediately above the gate. So you can see again, I have, well, maybe you can't see the arrow tip on the end there. It's up, whereas those other forces are down. So now the resultant force, we can use the square root of the sum of the squares to determine the magnitude of the resultant force. So if the horizontal is 98 and the vertical is 109, then we have 98 squared plus 109 squared. Take the square root of that. It's 146,870 newtons is the magnitude of the resultant force. All right. Now, we already found step 7, which was the line of action for the horizontal forces. So we know that this horizontal force is down, it was what, 5.0667 meters from the surface. But what about the location, the resulting location of the vertical forces? You know, there's this one, Fv, that's in the middle between B and C, and then there's W that's offset a little bit to the left. So we're going to talk about the location of those vertical forces. And just to refresh your memory, here's the line of action for the horizontal forces, where we were calculating YCP to determine that. The line of action for the vertical forces combined. So there is the rectangle, where it's just right in the middle, Fv, and then W is offset. And you can find the formula for the centroid of a quarter circle. And it's in our book. And that formula is 4r divided by 3 pi. And so the radius that it's talking about is the 2 meter radius that's defined, you know, the distance between C and B is also the distance from C to A. So r, the radius of curvature, is 2 meters, and that's the 2 meters that we put into this formula for the centroid. And always try, when you substitute numbers into an equation, ask yourself, is it reasonable? Like, does it make physical sense? The distance that this is describing, you know, 0.8488, that's talking about the distance from the left edge out to the center. So it makes sense that it would be less than 1, because 1 is what you get if it's a rectangle. But we are missing some of the area on the right side, and so because of that missing area, that shifts the magnitude, that shifts the location of W over to the left a bit. So it's, you know, not quite to the 1 meter mark where that force is applied. So the point of application of W is 0.8488 meters. And so now we have to find an average. Before I talk about the average, does anybody have questions about the location for FV or the location of W? All right. So how do you average two locations? Let me ask you this. Would it be correct if we're measuring from the left side? Let's say we're measuring from the left side. So it's 1 meter from the left for FV, and then it's 0.8488 meters for W. What would be wrong with just adding those two distances together and dividing by 2? That's the wrong approach. Who can tell me why would that be the wrong approach? To just add them together and divide by 2. I'm sure somebody's guessing at it. Just got to be bold and unmute the microphone. It's the most dangerous thing you can do these days. Go ahead.
Is it because the forces on each of them are different?
Exactly.
They have like magnitude tagged to them, yeah.
That's right. Very good. So, if the magnitude of the two forces were equal, then a simple average would be fine. But if one of these forces is really big and one of them is smaller, then that small force should be given less weight in bringing the average location over. And so we have to do a weighted average based on the magnitude. So what I'm saying is that the location of FV, 1 meter from the edge, is kind of proportionally determined by the magnitude of that force. And so I'm multiplying it by the magnitude of FV because I want it to, its location to count more than the location of W, because W is a smaller force, so it shouldn't count as much. That's what we mean by a weighted average. So I multiply the location by the magnitude and then divide by the sum of the magnitude. And so what that does is it brings the final location to 0.957 meters from C towards B. So what we're saying is from C towards B, the average location of the vertical force is going to be not quite 1 meter from that left edge. Okay, any questions before we move on this example to the next one?
Could we step back to the solution key?
Yep. Let's see, what part would you like to see?
The last part at the bottom.
Okay.
All right, I'm good, thank you.
Anybody else need to see a certain part? All right, so what did we learn in this example? All right, we learned that the resultant force F is the result of the vertical and the horizontal both. And so if you're asking how much of a force is required to hold the gate steady, the magnitude of that external force that must be applied is going to resist both the vertical forces and the horizontal forces. So that's one important thing that we learned. The next is that the horizontal force component is determined by considering the projected shape of the curved surface. And so in this case, the curve projected a vertically oriented rectangle. And we found the equivalent force acting on that hypothetical vertically oriented rectangle. So that's the horizontal force. And then the vertical forces we learned are just from the weight of the water. So you have to break up the overall shape. This is the original given sketch. So it's maybe not originally given with these dashed lines. You have to kind of fit the pieces together, or maybe break the pieces apart is a more accurate way to say it. You have to break the weight of the water above the gate into component pieces and then kind of calculate, all right, so what are the two different shapes that apply here. Let's apply that same technique to this next example. A curved gate. This time, instead of being concave, it's convex. So the gate is curving inward into the fluid in this case. And so what this is asking is, how big does F need to be in order to open the gate? And so think about what forces right now are keeping the gate closed. So there's going to be vertical forces acting down on the gate, and that's pushing on the gate in a counterclockwise manner. So that's keeping the gate closed. Also, there's the horizontal component coming in from the side, and that likewise is pushing in a counterclockwise rotation. And so that's keeping the gate closed, the horizontal component. And so if we're going to open up the gate by pulling on A and pulling up vertically, we're going to have some magnitude F that's acting at a moment distance of 3 meters from the hinge, because it's 3 meters out from B to where the force is located. And so we're going to go through the same kind of process that we did in the last example. We're going to consider the horizontal forces and the vertical forces, and then we also want to know the location of those forces. And so the first thing that you should be thinking when you see this is you should be breaking up the shapes for the water that's above the curve. So for example, we know that there's going to be, it says in this statement that the gate is 4 meters wide. So that means that above the gate there's kind of like a wedge shape, and then there's also a rectangular shape that's above that. And let me just show you. What I did was I thought of it like this. You know, there's 2 meters is the vertical distance from B up to the water surface, and then it's 3 meters from B out to the side. So that 3 meter distance is going to be one component of it, and then it's 4 meters into the page. Okay, so the forces, if this rectangular part is its force location is going to be right in the center, then the question is, what about the force component for this wedge piece? So does everybody see how I'm labeling B is just if there was water all the way over from B and then down. So if you haven't yet subtracted out under the gate where there isn't any water, then that's B. But now when we split it into the part that segment D is just where there's air, and segment C is the weight of the water that's above the gate. Hopefully everybody can kind of conceptually see what element C is. You know, there's a formula that describes the location of the center of area. 0.7766 times the radius is the distance from the right edge over to where that force is located. All right, so here's what I'd like you to do is find the magnitude of this force, the force that's coming from object A. Find the magnitude for this force, which I'm calling the force of object C. And then also there's going to be the horizontal force coming in from the side. And so think about what does the projection look like for that. And so the projection of this curved gate has what dimensions? Remember, it originally says it's 4 meters wide. So I'll pause for a moment, and I'd like you to get the calculator humming. Calculate the magnitude of this force, the magnitude of that force, the location of each, and then also the magnitude and location for the horizontal force. The horizontal force comes from analyzing the vertical projection. Okay, so the magnitude FA is going to be depending on the volume times the unit weight of the water. So what's the shape of A? 2 by 3 by 4 meters into the page. And so it's got a volume of 24 cubic meters that we multiply by the specific weight of the water in order to find its force. All right, so here is the magnitude of object A. So it's the 24 cubic meters, and the location of it is 1.5 meters from the left edge, and that's just kind of by inspection. If it is 3 meters in total width, and the center of area for a rectangle will be in the center, in terms of side to side. So it's 1.5 meters from the edge that force is located. So that is object A that's above the gate. And now object C that's above the gate, that's a little more tricky, right? Has anybody calculated yet what is the area of that shape? The area of shape C, or its volume? To calculate the area of shape C, then what you do is you find the area of like 3 meter by 3 meter rectangle and then subtract out the quarter circle. Okay, so we need to find out what's the volume of the water there. And let's see, Zachary's got it correct. Zachary has the force, what he's just typed in there, that's FC. So good job, Zachary, nicely done. Let me show you the solution for that part. Okay, so I'm dividing what I previously was calling, let me just do the silly animation here. All right, so object B is 3 by 3, right? So it's 3 meters tall, 3 meters wide. I split it up into its two constituent pieces. Piece D is the quarter circle, and C is what's left over. So if I find B and I subtract out D, then what remains is C. So in other words, C plus D equals B. Or the other way to say it is B minus D equals C. All right, so found the area and therefore also the volume of B, because I just take the area, multiply it by the distance into the page, 4 meters, and I get the volume. So that's the volume of object B. And subtract out the quarter circle of that. So it's a quarter circle times 4 meters of depth into the page. And so the area is the quarter circle, multiply that by 4, and so the resultant volume is 28.274 cubic meters. And then now what's left is piece C. And over here I've sketched out what piece C looks like. It's that wedge-shaped element of water that's above the gate, but not including the box of water that we've already accounted for. It's just that portion of water that's in the immediately above the gate. So we subtract out B minus D and get the volume of object C. Multiply that by gamma, and we get 75.7 kilonewtons. All right. Any questions so far on what we've found is the magnitudes? And we found the location of A. What about the location of C? Well, with this formula, that's pretty easy. I've calculated in a more complicated way in the past. I used this formula for calculating the location of the force at C, but that's become kind of tedious and a little too abstract. So instead, we'll just use this direct formula for the location of force C. And so here you can see the magnitude. This other approach that I used to use was kind of a weighted average. But instead of the weighted average approach, we get the same answer if we just calculate the distance directly. So it's 0.7766 times r, where the radius is 3 meters, and that gives us 2.328 meters. So that's effectively the same as the 2.33 that I used to calculate the bad old way when I was doing a weighted average. So we know the magnitude and the location for this force and this force. So that defines kind of, think about, we're doing a moment analysis about the hinge for B. We want to find out what are the forces that are pushing the gate counterclockwise, because we want to open the gate by pulling on it at A in a counterclockwise direction. So we've just found out how big is the force A and where it's located, how big is the force C and where it's located. And with those, we're going to be able to find kind of that moment that is causing the gate to be closed. But there's also the horizontal force that we have to account for. So the horizontal force is as though we are considering the vertical projection. And so this gate, its vertical projection is 3 meters tall and 4 meters wide. It may, for some of us, take a little bit of practice being able to visualize what the projection looks like. So if you have to, grab a piece of paper and look at it from different angles and convince yourself that, oh yeah, that curved gate has a height, a projected height of 3 meters and a width of 4 meters. So that makes the vertical component is B and the horizontal component is A. So 4 times 3 cubed divided by 12. Now, what about the magnitude of the force? The magnitude is going to be equal to the depth of the centroid multiplied by gamma times the area. So the depth of the centroid. So if the center of area for the projection is 2 meters plus 1.5 meters. So the delta H is equal to y bar. It's 3.5 meters down from the water surface to where the centroid is located. The little sketch that's to the left of that kind of illustrates it's 2 meters from the water surface to the top of the projected gate, and then half the distance of the projected gate from the top to the center of area. So the magnitude of the force is 412,000 newtons. And then the location of the force we calculate from the YCP. Depth of the centroid, y bar is the same as delta H because it's vertically oriented. So you can see that the YCP 3.71 meters. Okay, now the overall answer that this example is asking is, what is the force on the gate? What force is required to open the gate? So we've calculated this force that's keeping it closed, this force that's keeping it closed, and now also the horizontal force is keeping it closed. But now we have to balance that all out with the force that's required to open it. So FA was the weight of the water in the rectangular element. FC was the weight of the water in the wedge-shaped element. FH is the hydrostatic force having to do with the pressure at a certain depth acting over an area. And then F is going to be us pulling upward in order to open the gate. And so you can see the applicable distances there. FA is 1.5 meters is the distance sideways over to where the force is located. 2.33 meters is the distance sideways over to where FC is located. And now FH, we want to know what is the distance from the point of from the hinge down to where the force is located. So that's the vertical distance. And it's 2 meters from the water surface to B, and the overall distance that we'd calculated here was 3.71. So 3.71 minus the 2 meter distance. So what's going to be left is how far below B is that force located, F sub H located. So here you can see I'm setting up the clockwise rotation on the left. So F will be pulling the gate open. And then the counterclockwise rotation effects on the right. So all three of those forces are acting to keep the gate closed. And so the only unknown now is going to be F. Everything else is determined previously from our analysis. And so that means that F will be 412 kilonewtons. All right. So this second example is the last one that I have for you today. Are there any questions that I can answer about certain parts of why we did a certain thing or numbers that you need to see again? Is there anything that we can take a second look at before we can conclude for today? Well, thanks for joining the lecture. I know that, boy, these online lectures must be pretty tedious. Just sit in front of your computer all day, every day, and I really am sympathetic because it's not the learning experience I wish you were getting. It's not the teaching experience that I want to have. I really prefer it if we're able to be in the same classroom together. And so I admire your discipline. I admire your persistence of sticking with your education when you're getting it under difficult circumstances. But I'm convinced that it's still possible to learn. And so try and stay hopeful, stay positive. We'll get through it together. Let me just wrap up with a couple of final announcements here. Remember that Thursday's class meeting is going to be pre-recorded, so I'll send you the link to that. But we won't be meeting live virtually that day. And your next homework assignment is available now if you want to get an early start. It includes questions related to what we covered today, so I'd encourage you to get started on that. And then I intend to give you some additional information about the exam as we move forward, but I just introduced the idea that you're going to have a little bit of extra time on either side of our class meeting. And then, all you'll really need, if you were going to take it in the classroom, I'd expect some students would probably finish as quickly as 40 minutes, maybe 45. And you've got 75 minutes of class time, and then additional time on either side of that. So I don't anticipate that a time limitation is going to be a critical factor as long as you know the material. All right. Have a great day. Thanks again. I'll see you in the lab tomorrow or today.